Okay, so today we're going to focus on, we're going to do all of section 4.3. 4.3a right now, and then 4.3b soon. I wouldn't say that you need to write this down right here. I'm going to talk about it, but you might want to at least write down what the section is called. Okay, so finally today we get to mash everything together from what we've learned and actually talk about what things mean. Okay? So we did this big idea of integrals, and then we did this big idea of area under the curve. Okay, how do they relate to each other? Now, first of all, that quiz that we just finished, where are we getting exact area? No, we were approximating area under the curve using either rectangles or trapezoids. Okay, we were either getting an over approximation or an under approximation. Okay, well now, if we make more rectangles, our work becomes more tedious, but our area becomes more accurate, right? Okay, well what if we could increase our number of rectangles infinitely, okay? What if we talked about infinitely many, infinitely small rectangles? What do you think would happen to our area? It would actually be accurate. It would be the area, okay? So we're going to take the idea of our approximating with rectangles, and we're actually going to use it to find the exact area, okay? We are going to do that by summing up an infinite number of infinitely small rectangles, okay? So go ahead and write this down. Our exact area is going to be this. Okay, what is all this? What does this mean? Sum. We're summing up length times width infinitely many times of infinitely small rectangles. So we are going to have to go back to some of our limit rules, which we will review. But if we take the sum of our rectangles and we take that limit towards infinity, we're talking about making those rectangles infinitely small. And we're talking about infinitely many rectangles. So basically we're just finding the area of those lines that would fit underneath. Okay, and now we have an exact area. Okay, we're going to get to how we're going to do this pretty soon, but how does this have anything to do with integrals? Okay, here's where these two get to match together. Okay, the definite integral from a to b. Okay, so we talked about indefinite integrals, like just a symbol. So now we're going to put numbers there. The definite integral from a to b is telling us this is the area under the curve. Okay, so what?
I said Mr. Gaffney spoiled these.
Oh, did he?
Yeah.
Dang it. It's okay. Okay, so I just talked about this being the exact area. This is also what it means. The integral, now we have numbers from a to b of our function dx is calculating the area under the curve. What?
said this is like every concept we've done this year.
Do you know how much I've forgotten?
Okay. Shall we flash back to Unit 1 and talk about some limits real quick? Also, I want to bring in some of the concepts from the quiz that you just took. You know those summation formulas that we have? We're going to need those to help us in conjunction with our limit rules. Okay? So we are going to go through 4 different scenarios that are going to pop up in our Riemann sums. Okay? Scenario number 1. The limit of the sum, where we have 1 over n, the constant taken out, and we're summing up 1 inside. Okay, question. What's the sum from k equals 1 to n of 1, n? What's 1 over n times n? And what's the limit as n approaches infinity of 1? 1. Okay. That one wasn't too bad, because everything just canceled out. Okay. Let's talk about our shortcut for when we have k inside of our summation. Because of what happens with our Riemann sums, if you are summing up k, then you more than likely, by more than likely you will, have a 1 over n squared that we can take out of the summation. This is a constant because k is what our index is. Okay. Okay, so when we take this limit, we have 1 over n squared, and then the summation of k from 1 to n. What was that shortcut? Over 2? Okay, let's flash back to our limits. Okay, what's true about the degree of the numerator and the denominator? They're the same, which means we can look at the coefficients for our horizontal asymptote. And if we're taking a limit towards infinity, then the horizontal asymptote is what we need to look at. Where is our horizontal asymptote? If we multiplied this out, what would the coefficient of n squared be? If we multiplied this out, what's the coefficient of n squared? So 1/2 is our limit. That's where our horizontal asymptote is, so that's what we're approaching as we go to infinity. That's nice. Let's talk about our k squared shortcut. And if you have your k squared summation, then you're going to probably have a 1 over n cubed out in front, which will help as we evaluate the limit, but write it down first. So we have the limit as n approaches infinity. 1 over n cubed is our constant that we've already pulled out from the summation. And then we have a shortcut. if we have the sum from k equals 1 to n of k squared, then we know that that is going to be n times n plus 1 times 2n plus 1 all over 6. Okay, we have a fraction, and we're approaching infinity. We can think about the horizontal asymptote for our limit. If we multiply this out, what's the degree of our numerator? Okay, we have a third degree in the top, and in the bottom, a third degree. So we can look at our coefficients. If we multiplied this out, what would the coefficient be of n cubed?
2.
And of the denominator? So 1/3 is our limit. All right, Alex is saying our next one's going to be 1/4. What do you think?
I hope he's right.
You hope he's right.
Yeah.
This is our last one. All right, so we have the limit as n approaches infinity of 1 over n to the 4th. When we have the summation from k equals 1 to n of k cubed, our shortcut is n times n plus 1 all over 2, the quantity squared. All right, we multiply everything out. What is the degree of the numerator? Okay, we have a 4th degree upstairs. What about downstairs? A 4th degree. So since we're going towards infinity, we can look at the coefficients, and that will tell us where our horizontal asymptote is. What is the coefficient of n to the 4th in the numerator? How about the denominator? Alex, we've done these limits. We've got through them. So when they occur in your work, I'm hoping they won't have to take much thought. Okay? We can kind of go through the motions like we did right here. Now, put your pencils down for a moment. On this next slide, I'm just going to talk and you're going to listen. Okay? And we can maybe talk back and forth, but I just want to put the big idea together. Okay? So this is what is going to happen. For our Riemann sum, and that's like the first thing that we looked at, that the limit of the sum, okay? We are going to take a closed interval from A to B, okay? And we have a function there. And what is going to happen is we are going to partition the interval. What does partition mean? Break it into pieces or parts, right? Partition, we're breaking it up into parts. And in this case, we're breaking it up into infinitely many parts. So we're saying n parts, but we're taking the limit as n approaches infinity, which means we're breaking this up into infinitely many parts. Okay? All the way from A to B. Okay? Okay? And so we are going to let the width of our itty bitty intervals be delta x of I. All right? Basically, delta x is what you need to think about. Okay, that's the width of each of our intervals. And then how do we find our rectangles? We take our width times our height. And when you did your quiz yesterday, how do you get the height of your rectangles? What do you do with delta x? How do you get the height, just in general? Plug it in to get the y value, right? Our f of x. Okay? So that's where this is coming from. Okay. Why is it doing that? Okay, whatever. This is the function value for whatever little subinterval we're on. Delta x, that's our width. Okay. So then we take the limit towards infinity of that sum, and we have the exact area under the curve from A to B. Okay, this is a slide I've already had up here before. Okay, this is the math behind what is going on. All right, now we talked about right hand, left hand, and midpoints for our rectangles. Okay, when we do these Riemann sums, we are always going to use right hand endpoints. Okay. Okay. Since that is the case, when we talk about x sub k, I want you to think about how you did your quiz. When you took a right-hand endpoint, if our interval is a to b, did you plug in a? No. We plugged in b and we worked our way this way, correct? So really we began with a plus delta x, right? If we think about our interval, whatever delta x was, a plus delta x was the first we plugged in on that side. So I want you to write this down, okay? Wherever you have this right here, I want you to write this down. When we do our right-hand approximations, we take A and we add delta x, and then we add 2 delta x, and then we add 3 delta x, and then we add 4 delta x. You see where I'm going with this? That's why there is a k there. But for our right-hand endpoint, we don't start at A, we start at A plus delta x. And so this is just going to describe at any part of our interval, we are A plus some delta x. Okay, that's going to make our math a little easier if we use it with the right hand. Okay, so my goal for right now is to do 2 examples. One fairly simple, one just a little bit more involved, but not by much. Okay, depending on the time, I think we'll be able to have a little bit of work time on your homework as kind of a break before we go into the next set of notes. Does that sound okay? All right. So, example number 1 of 2. Y equals x squared. And we're going to be on the interval from 0 to 5. Okay. So, I have a picture of what we're finding. If we're talking about y equals x squared, here's my parabola. And then the area from the interval 0 to 5 is shaded in that maroon color. Okay? So what we are going to find is the integral from 0 to 5 of x squared dx. That's what we are going to calculate. Now, just like we did with our rectangles, we need to calculate delta x. And how do we calculate delta x? We calculate it by taking b minus a over n, right? Well, b minus a would be this 5 minus 0. N is going to have to stay as n for our Riemann sum, okay? Because we're going to take the limit as n approaches infinity, we're going to get an infinite number of rectangles. So we'll leave it as n. So 5 over n is going to be our delta x. Also, we need to determine what that x sub k is going to equal. Remember, I asked that you make x sub k a plus k times delta x. Okay. Well, in this problem, what is our a value? What's the very beginning of our interval? 0. Okay, that's why we're starting off with this problem. Okay, a is 0, k is k, and then our delta x is 5 over n. So we are finding the exact area under the curve of x squared from 0 to 5. So this is what that means, the integral from 0 to 5 of x squared dx. And what we're going to do is we're going to take the limit as n approaches infinity of the sum from k equals 1 to n of f of x sub k delta x. Okay, this is what we wrote down on that second slide, right? Well, now let's actually apply that to what we've got going right here. So what we need to do is we need to plug x sub k, well that's right here, into our function f. Well, our function f is x squared, so I'm going to plug this guy, 5 over nk, into our function x squared, and then that needs to be multiplied to delta x, and delta x is 5 over n. Are you okay with how I set that up? Where I got all of those values from and why? Yes. Well, it is a k, but it's so small. It just kind of looks like gibberish right there, doesn't it? Is that better? All right, so now let's make this look a little bit nicer. We have the limit as n approaches infinity of the sum k equals 1 to n. What do we have? We have 125 over n cubed times k squared. We have 5 squared times 5, and we have n squared times n. Are you okay with how I wrote that? All right, so now I know that since I'm adding up from k equals 1 to something, this 125 over n cubed doesn't matter, right? But we do want the sum of k squared. What is the sum of k squared? Okay, we already know what this limit is. We already know that this limit right here is what? 1/3. So what we have is 125 times 1/3. And ladies and gentlemen, that is our exact area for the interval from 0 to 5 of our curve x squared. questions or clarifications before we do a second problem? Okay. The algebra in this is going to be where you need to be careful. Okay? The calculus really isn't so bad. It's just a limit at the end. It's the algebra that you need to be careful with. So let's do our second example. So we have 4 minus x squared on the interval -2 to 2. So I have a picture of what we're finding. We're finding that area. You will need a little bit more room for this one. Probably double the space from what it took you. All right. So let's find something. Delta x. Delta x, we have to take b minus a over n, but this time n just stays as our delta x is 4 over n. We also need to know what x sub k is. And since we are doing our right hand approximation, well, not approximation, but we're setting it up with right hand rectangles, then we need to start with a and add k times delta x. Okay, so we know that the integral from -2 to 2 of 4 minus x squared dx means, yes.
So when you first put down x is k, x,
Mhm.
always write on the right hand.
Mhm.
So does that not matter? It's like we choose the left.
Well, when we do right-hand approximations, we never start with the left side of the interval. We always start with the left plus delta x so we can get the right side of that rectangle. So for each of the rectangles, we have to take the left side and add delta x to it to actually get the side of the rectangle that we want. Do you see what I mean by that? Do you want me to do a numeric example to show you? Okay. Like if we had let's say we had the interval from 3 to 4, and our delta x was 1/4. Then what we would do for a right-hand approximation is we would take 1/4 times f of 3 1/4 plus f of 3 2/4 plus f of 3 3/4 plus f of 4 to be on the right hand of each rectangle. We never used 3. We had to use 3 and a little bit more. And then delta x more and delta x more. Alex, you okay with that?
Mm-hmm.
Here's, okay. All right. So now, we are going to take the limit as n approaches infinity of the sum from k equals 1 to n. What goes inside? Inside, we have to have f of x sub k times delta x. So I'm going to do this first. Put my delta x first. That's the easiest to write. But we need to multiply it by f of x sub k. Well, our function is 4 minus x squared. So 4 minus, plug in x sub k for our function. So 4 minus x squared. I know when we get to the end, you can do limits. And I know you know how to do all of this algebra, but this is where we need to be careful because the algebra gets a little bit messy. Okay? So have some patience. Where would be a good place to start in our algebra? The square. Okay? I don't think we need to write this down, but I'm going to write this down for reference. We are taking a binomial times itself, so we are going to have to FOIL. I don't like that word, but I'm going to use it because I know you're comfortable with it. Okay, so when we multiply that binomial out, negative 2 times negative 2 is 4. Negative 2 times 4 over nk is negative 8 over nk, but we get that twice because we are multiplying a binomial times itself. So I'm going to go ahead and change that to negative 16 over nk because we know we're going to get that twice. And then our last 4 over nk times 4 over nk would be 16 over n squared k squared. Okay, we're almost there. Okay, so now when we perform this subtraction, the 4 minus 4 goes away. We are subtracting, so this becomes a positive 16 over nk minus 16 over n squared k squared, all multiplied still by our delta x. Yes, I do. Sure. Mr. Grill, I bet it's about that. Okay. So this is what I'm going to do. I'm going to go ahead and break this up into 2 because we have 2 parts to it. So let's go ahead and distribute this through, and I'm going to break it up into 2 pieces. So this first portion, when we carry that through, what we would have 64 over n squared times k. And then I'm going to subtract the limit as n approaches infinity of the sum, k equals 1 to n, of 64 over n cubed k squared. The end is near. 2 steps. We have 2 steps left. Okay? The 64 over n squared does nothing for us. But we do have the sum from k equals 1 to n of k. Well, we know that that shortcut sorry, trying to get it. We know that that shortcut is n times n plus 1 over 2. And then we're subtracting the limit as n approaches infinity. The 64 over n cubed means nothing in our summation, but we do have the sum from k equals 1 to n of k squared. And we know that that is n times n plus 1 times 2n plus 1 over 6. So we've already talked about this limit right here. What did we say it was? 1/2. And then we've already talked about this limit right here. Is 1/3. So we have 32 minus 30, 64 thirds. Which if somebody wants to just put that into their calculator real quick for me. And give it to me in fraction form, please. 32 thirds? Okay. All right. Now, I know that this is very involved, okay? Which is why I want to give you some time right now to do some problems. So, on your gold sheet, it's actually the homework assignment for 124. It's the assignment for 124. I'm going to go ahead and say, I'm going to give you until 11:15. I'm going to give you 20 minutes to start that assignment, which means I hope you can get a few of these. You're not going to get it all the way done in 15 minutes, 20 minutes, okay? But we'll at least get a start, and if you have questions, I'm here to guide you, all right? So, until 11:15, I want you to get out a book, start to work on that 124 assignment.